Hello BC Calculus students, this is Mr. Johnson and this is section 2.7 which is on the derivative as a function. For the class opener what we'll do is draw a diagram showing the definition of a derivative in the two different forms that we tend to use. I'm going to pause the video and draw the diagrams. Okay, so here we have our two diagrams that you've all seen many different times. On the left we have the definition of a derivative with respect to h. So if we were to look at this particular set of points on a graph and the distance between the 2 points is going to be h, if we were to let that value of h approach 0, then what happens is we go from a secant line between 2 points to a tangent line at 1 point. So we have the limit as h goes to 0 of the second y value f of x plus h minus the first y value f of x divided by the distance between the x values, which we have called h. So this is one of our main definitions of a derivative. This is usually the first one that you learn, and this is also, it tends to be the most common one. Over on the right side, we have the other one. So in this case, we have the situation where we have these 2 points. One is labeled a and one is labeled x, and of course those are complete dummy variables, so you may see something different than those. And we take the limit as x approaches a, so as we go from a secant line and we approach that point at a, making it a tangent line, we have the second y value f of x minus the first f of a, and we divide that by x minus a. And this is technically the derivative at the value a, which again, a is a complete dummy variable. So these are the two different definitions of a derivative that we not only need to have memorized, but we have to know how to take these particular definitions and identify the correct function, but also identify the value or where the derivative is being analyzed. So we have to know how to use these really well, because on the exam, it can be common for them to utilize this technique in such a way that they're asking for the derivative, but they don't call it explicitly a derivative in the problem. So this is just, two different sets of notation for derivatives. So what are some other notations that we need to know for derivative? And there are actually a lot more than 4. The most common, we have f prime of x. We've seen that a lot. Of course, we have y prime. That's another one. Leibniz notation, which is dy dx, is often throughout the exam, especially with differential equations. You also could have d over dx of f of x. You could have just d of f of x, which I have not seen much on the exam at all, or d sub, that means with respect to x, you're taking the derivative of f of x. Again, those last two are not super common. But when you look at these different notations, one of the differences with a notation such as this one here with the d over dx, that d over dx isn't a derivative on its own. It's an operator. So it's like having a square root symbol or a division symbol. That d over dx tells you to take the derivative of f of x with respect to x. But anyway, what I would say is that all of these 4 here, those are the 4 that are kind of the main derivative notations that we've used over the last year or so, and you will see again this year. Okay, let's talk now about differentiability, or whether or not a function is differentiable, whether or not a function has a derivative. The definition says that a function f is differentiable at a point a if simply f prime of a exists. And so when we're looking at this, a function is differentiable on this open interval. Let's say the interval is a to b as the definition dictates. Then the function, if it's considered differentiable, is differentiable at every single point, every single number on that particular interval. So we're going to look at the absolute value of x graph. I'm not going to look at the sign of x right now. I want to just illustrate a point for the absolute value of x. So first off, some of you may remember the definition of the derivative of the absolute value. And the one that we had you memorize last year was x over the absolute value of x, or you also could put absolute value of x over x. They're equivalent just because of the fact of how it's set up and the fact that you have the x, in terms of the numerator and denominator. But I'm going to show you or remind you maybe of how we get that derivative. So let's say that we want to let f of x equal the square root of x squared, which is equivalent to the absolute value of x. You can graph it on your calculator to convince yourself. I'm going to write this as x squared, that quantity, to the 1/2 power. So if we take the derivative, we're going to apply the power rule and the chain rule. So the power rule says we have 1/2 times x squared to the negative 1/2 power. Chain rule says we multiply by 2x. Now this can simplify because the 2 and the 1/2 cancel, and if you take a look at the exponent and make it a positive one, you have x divided by the quantity x squared to the positive 1/2, which again we defined as the absolute value of x. So that's one of the ways to develop the definition of the derivative of the absolute value of x. Now here's the question that we're asking, because we're talking about differentiability. So if we were to look at a graph of the absolute value of x, we know what it looks like, and we also know based on last year that it's not differentiable at 0. And the reason that we would say it's not is because there's a sharp corner there. If you have some sort of graph with a sharp corner or some sort of immediate change in slope, the derivative can't exist, because on the left side of that, let's take a look at that really quick. We have, let's see, the derivative, or the limit as h goes to 0 from the left of the absolute value of 0 plus h minus the absolute value of 0 over h. So what I'm doing is I'm using the definition of a derivative we did in the opener, and I'm approaching from the left side of 0, we're going to get negative 1. If, however, we look at the limit as h goes to 0 from the right, the absolute value of 0 plus h minus absolute value of 0 over h, we get positive 1. So what's happening is that when we look at the absolute value of x graph, the slope on the left of 0 is negative 1. We can see that in just a linear sense. The slope on the right is positive 1, and therefore if we were to graph the derivative, so here is our original function f of x equals absolute value of x. If we were to graph the derivative, we would have an open circle and we would have a slope, or a value of 1 when x is greater than 0, and a value of negative 1 when x is less than 0. And this is sort of a visual of the fact that the derivative does not exist at 0, because again, when you're looking at the slope, there isn't a gradual change in the slope. There isn't a way of looking at the value of 0 on the absolute value graph and getting some sort of tangent line like visual from it. It's always going to have this angle to it, this V. There's never going to be a nice smooth slope there. So for instance, if we analyze the idea of the square root of x, if we look at y equals x squared and we focus on the origin this time, if you were to zoom in on that, it actually looks linear at that particular point. And so the slope there is 0, because as you approach it from the left and as you approach it from the right, you end up getting this gradual change in slope from a negative slope to a positive slope that's unlike the absolute value graph, that is just an immediate and distinct change in slope. Okay, so in terms of the whole idea here of differentiability, a differentiable function is differentiable for every value on its particular interval. And that means it does not have any discontinuity, it doesn't have any breaking apart of the graph, it doesn't have any sharp corners, it doesn't have any vertical tangents, it has a slope defined at every single point on the particular interval. Okay, let's go on to the next page. So I mentioned the connection between differentiability and continuity, because I mentioned that if you have a discontinuous graph, then you cannot take a derivative at every single point, because the function itself completely changes. But there's a theorem in our book that says that if f is differentiable at a value a, then f is also continuous at that value a. And that is a very intuitive theorem. We know that if the slope exists, well, then the function must exist, it must be continuous. Now the converse of the theorem is this. So we have, if f is continuous at a, then f is differentiable. And this is such a common question on a multiple choice set where they say which of the following is true or which of the following is false. They constantly try to catch people on this kind of idea. The converse is absolutely false. If f of x is continuous at a value, it does not guarantee it's differentiable. The simple example you could use is the one we just talked about with absolute value. Absolute value is continuous. However, when x is 0, it isn't differentiable. So what functions are not differentiable? Well, I've kind of mentioned them already as we've talked. So I'm going to write these, I'm going to pause and then write these out for you. Okay, so there's really three that we focus on here. So the first one is discontinuous functions. One example of that would be something like the greatest integer function that we discussed in a previous lesson where you have sort of this step function. It's discontinuous, and since it's discontinuous, that means that the derivative does not exist at every single value, or that it's not a possibility for the derivative to exist. The functions with vertical tangents. So one of the examples of this would be something like y equals x to the 1/3 power. And this type of function looks like this, where there's actually a portion of it that basically becomes vertical at one point. And it can be really difficult to see that on a graph. But if you were to take the derivative, you'd find that, wait a second, there is a spot where the derivative does not exist. In this case, for the example I just gave you, it would be when x is equal to 0. And then you have functions with sharp corners. And again, the example we just discussed recently is the absolute value of x. That's an example of where you have a sharp corner, therefore it's not differentiable for every value. Now, how do we know? This is something that I mentioned on the first page of notes for this section. But if you were to take something like y equals x squared, and you were to look at any point, let's just look at the origin. If you were to zoom in on that origin, really, really, really close, you would actually get this picture of almost a linear graph. It would look just like a line. That linear portion that you're seeing is actually a representative of the tangent line. And that is one way that we can sort of visually see whether or not something is differentiable. Versus if you have the absolute value of x graph, okay, and you zoom in on x is equal to 0, no matter how close you get, you will never see this nice tangent line-like behavior to the actual function at that point of 0. You'll always see some sort of V shape to it, some sort of sharp corner. Okay, let's try some examples. So at the beginning here of the lesson, I mentioned that your two different definitions of a derivative are so important. They come up a lot in problems in our class and last year as well. Here's an example of that. So this problem is really screaming to you, what is the derivative? Now, as you practice, you'll pick up on that more often. But in order to answer the question, we need to figure out a couple pieces of information. The first thing is we got to figure out which function are they actually talking about. The second thing is which x value are they referring to, and from there we can actually take the derivative. Now remember, you have the limit as h goes to 0 of f of x plus h minus f of x over h. So your goal here is to sort of line things up. It's really clear to me as I look at this that 4 is in the place of x in the general definition. So I'd say that we're evaluating this when x is 4. And not only that, but it's pretty clear that if 4 is in place of x, the function then is the natural log of x. Okay, if that's the case, then we have a derivative, which is 1 over x, and we're going to evaluate the derivative at 4, which is option B, 1 over 4. Okay, let's take a look at example 2. So we're going to do a little bit of particle motion, which we have done recently here in our sections for chapter 2. So it says if t is greater than 0, the position of the particle moving along the x-axis is given by x of t. What is the acceleration of the particle at the point where the velocity is first equal to 0? So remember, when we take the derivative of position, we get velocity, and that is cosine t plus sine t. And we want to know when is the velocity first equal to 0. So we set velocity equal to 0, which means that what we're looking for is when cosine and sine are opposite signs. So to me, what I do is I think about the graphs of them, but also some of the important angles that we've studied with regard to these particular functions. And the angle that we're looking for when they're the same is pi over 4. So for instance, in the first quadrant, you have pi over 4. That's going to give you the same value for cosine and sine. The next time that they're the same value, except opposite signs, would be 3 pi over 4. So that's what we're looking for in this case. Okay, from there we need to find the acceleration, which is going to be the second derivative of position, which is the first derivative of velocity. That's going to be negative sine of t plus cosine t. And in this case, what we're going to do then is substitute in 3 pi over 4 for the acceleration. And what we get is negative sine of 3 pi over 4, which means we get negative root 2 over 2. And cosine of 3 pi over 4 is actually negative. So we have negative square root 2 over 2, which gives us a total of negative square root of 2 over 2 minus square root of 2 over 2, which means we get just simply negative root 2 when we add up those two halves. And that is option A. All right, let's move on to the next page. For example 3, we're looking at the idea of differentiability, which we've talked about a lot, continuity, which we've talked about a lot. And so when you look at this particular function, we don't necessarily know exactly what it looks like. It's a non-calculator problem, so we're not really expected to graph it. But it says which of the following are true. So the first one is f is continuous, but not differentiable at x is equal to 2. Okay, that seems pretty tempting to me because I'm trying to think through, at 2, if we were to plug in 2, we would get 0, and absolute value of 0 is fine, and the square root of 0 is fine. So f is continuous at 2, but I would say it's not differentiable because no matter the square root, the absolute value is going to have a sharp corner at 2 because that's where the vertex is. So A is pretty tempting. F is differentiable at 2. We disagree with that because, again, we're looking at something that has some sort of sharp corner. F is not continuous at 2. No, it definitely is continuous at 2. The limit as x goes to 2 of fx is not equal to 0. Well, remember, if you plug in 2, you get 0. So therefore, the limit is equal to 0. And then x equals 2 is a vertical asymptote of the graph of f. Think through with vertical asymptotes, you're looking for the denominator equal to 0. In this case, we don't have that, and not only that, but when we plug in 2, we get 0. We get a number. We don't get a vertical asymptote. So here we go. We have A. F is continuous, but it's not differentiable. You cannot take the derivative at 2. All right, we have example 4, which is another definition of the derivative, and this one is using h again. So remember, the limit definition is equal to f prime of x. So what they're doing in sort of a fancy way is they're telling you what the derivative is. It is 1 over square root x. Now we're also given information about f, which it says f contains the origin. So that means that f of 0 is equal to 0. So we have the derivative, we have 1 point on f, and we're trying to find f of 9, which is another point on f. So let's take the antiderivative of 1 over square root x, which is the derivative. This will give us the function in general, so plus c. I'm going to make this x to the negative 1/2 power because we're going to use the power rule. So to find this, we add 1 to the power, so we get x to the positive 1/2, and then we divide by 1/2. So we get 2x to the positive 1/2 plus c. Now remember, this is f of x now that we're finding. We need to find c. So we're going to plug in 0 and 0, which we know is a point on the graph. So we have 0 equals 2 times 0 to the 1/2 plus c. That would imply that c is equal to 0. So now what we have is f of x equal to 2x to the 1/2 power. That's our function. And we're simply just trying to calculate when what f is when x is 9. So we have 2 times 9 to the 1/2, and that gives us 6, which is option D. Okay, our last example. This is one of my favorite examples. I think it is very confusing, and I think that plenty of people get it incorrect because there's a really strong distractor in here. But then I think a lot of people actually get it correct, but for the very wrong reasons. So bear with me as I go through this problem because I think it's a really interesting one and quite complex. So what we have is a piecewise function. I strongly recommend graphing this, or at least thinking about the graph when you look at problems like this, because I think that, and I'll show you where the distractor is, but I think it can be very misleading if you just kind of rely on trying to think through it rather than actually see it. So in this case, and actually, you know what, let's do this first. So if you're trying to analyze the derivative, I think a lot of people think that 3 is true. And if 3 is true, that means 1 and 2 are true as well. So I think a lot of people put D, and that is incorrect. And here's why I think that. So if you were to take the derivative in piecewise form, the derivative of 2x minus 2 is 2. And the derivative of 2x minus 4 is 2. And so I think a lot of people say, well, therefore, the derivative is 2. And I understand completely why people are doing that. However, you have to think about what's actually happening to the graph itself. So let's graph it. So we have, let's see, so 2x minus 2 when x is 3 is going to give us 4. So that's going to be here, open circle, it's going to go that way. And then 2x minus 4 at 3 is going to give you 2, which is right here. Now, both of these little lines here, or segments I should say, have a slope of 2. However, it's not continuous. Therefore, 3 is completely gone. We cannot deal with 3 at all because the graph itself is discontinuous. All right, now the question is it 1 or is it 2? It can't be both. It can be both, actually, I guess, because C is 1 and 2. But which one is it, or is it both, I guess? Now remember, the first one is really looking at the left of 2, and the second one's looking at the right of 2. So this is going to be f prime on the left, and this is f prime on the right. I think one tendency for people is to say, well, the derivative on the left side of 3 is 2, and the derivative on the right side of 3 is 2. And that's absolutely correct in the sense that the slopes are 2 on either side of 3. The problem is, if you think back to some of the definitions in this section, for something to be differentiable, it must be continuous. Now, we know that the entire function is not continuous. So if you were to ask the question, the limit as h goes to 0 of f of 3 plus h minus f of 3 over h is equal to 2, the answer would be no, because remember we talked about it right here in part 3 that this particular function is not continuous at 3. Therefore, you can't actually calculate the derivative. Okay. However, with parts 1 and 2, we don't have a two-sided limit definition for a derivative. We have a one-sided limit definition for a derivative. So we're going to take a look at our graph here, and we're going to determine, is it left continuous or right continuous? So if we're looking for left continuity, and this goes back a couple sections now, but it's a really complex idea, but this is the way you have to answer this question. So left continuity is going to say that the limit as h goes to 0 from the left of f of 3 plus h minus f of 3 over h is equal to f of 3. And right continuity is going to say that the limit as h goes to 0 from the right of f of 3 plus h minus f of 3 over h is equal to f of 3. All right, so which one's true? Well, if we look at our graph, f of 3 is 2, and the limit from the left is approaching 4. Therefore, it is not left continuous because these two values are not the same, the limit and the function value. However, from the right side, if we analyze this portion of the graph, the limit as we approach 3 from the right is 2, and the function value is 2. So this shows that this particular function, when we analyze 3, is considered right continuous. Now, if it's continuous from the right side, then by definition, the derivative from the right side can exist. So the answer to this problem is going to be option 2. And again, the reason for that is that because the function is continuous from the right side, it's a right continuous function, the derivative from the right side does exist and is equal to 2. Now, one of the really confusing parts to this is that the 2 that is shown here is actually the slope, not the y value. I know that if you look at the graph, the y value right here is 2, but remember this is the definition of slope, which means that it's acknowledging that the slope is 2, but the reason that 1 doesn't work is because it's not left continuous, it's right continuous. So again, this can be a very confusing problem, I think, but I hope some of that makes some sense. Obviously, on any kind of multiple choice question like this, it's supposed to be about 2 minutes on average, and this one could easily take you about 10. Anyway, that is our section 2.7. Thank you, and we'll move on to the last section in chapter 2 shortly.